Hello and welcome to another video in this series as we journey from the very simple primes to the foothills of the very famous Riemann hypothesis. Today we're going to be doing a bit of an appendix kind of video where we're going to dig a little deeper into something that we glossed over perhaps a bit naughtily in a previous video. And essentially what we did there was we swapped the limit of a sum for the sum of a limit, and we didn't talk about it too much then, but I feel like we need to explain it a little bit better, so that's what this video will be about. So let's dive into where this question arose. So we took the Riemann Zeta function into the complex plane and we visualized it, and we talked a lot about where it converges and what it looks like. One of the things we noticed was as the real part of S increases, as in it moves to the right of the complex plane, the Riemann Zeta function looked like, at least its magnitude, looked like it converged to 1. And we did a little bit of algebra to show that that was the case, but we kind of glossed over a detail. So that's where this this question arises. Let's remind ourselves about what we did. So this is now the familiar sum 1 over n to the s. That's the series representation for the Riemann Zeta function, and that's valid for the real part of s being greater than 1. We now know that by heart, we've talked about it so often. By the way, if you've just joined us, do go back to the early videos because they take us on that journey from scratch almost. So if anything today confuses you, do go back to early videos to see if the answer's there. So this is the famous sum, and we ask the question, what happens when sigma, which is the real part of s, grows towards infinity, plus infinity to the right? And we said, well, yep, that's the limit as sigma goes to infinity of this infinite sum. And what we said previously was that if we look at each individual term, 1 over 1 to the s, or 1 over 2 to the s, or 1 over n to the s, the magnitude of that, which we've previously shown, is n to the minus sigma. We've shown why that's the case 2 or 3 times now, so I won't do it again. It's very easy. And then we can easily see that as sigma gets larger, the magnitude of the terms goes towards 0. And that's really handy because it means all these terms, the magnitude of them, irrespective of the imaginary part, the complex part, the magnitude goes to 0, which means they disappear as sigma goes to infinity, except the very first one, which is 1 to the s is 1. So we concluded there that what happens to this infinite sum is that as sigma goes to infinity, all the terms except the first one gets smaller towards 0 and in effect vanish in the limit. And that's really that's a really nice analysis. It's convenient. It feels quite neat. But actually we actually glossed over a little complexity. What we did was we said here the limit is outside the sum, quite correctly, because that's the real question. What happens to this quantity as we take the limit sigma to infinity? What we've done by doing this analysis is take effectively the limit inside the sum by applying this limit to each term individually, and then doing the sum outside. Now that might feel intuitively correct, but actually it's only always true for finite sums. It's not always true for infinite sums, and therefore we have to justify it. So it felt correct and easy, but to be proper, we have to explain why we were allowed to do that, and we didn't do that last time, so we're going to do that today. So we're just saying here that the limit of an infinite sum is not always the sum of the individual limits. That's something that's not always true. And there's a theorem called Tannery's theorem, and it's really useful. It's not that well known for some reason, and I think it's because there are more general theorems that people use, and this is a special case of those. But it's a nice one that isn't overly complicated, so we'll look at it today because it's handy and useful for the kinds of things that we'll be looking at. And it tells us when we can safely swap the sum and the limit operators. So what we'll do is we'll state the theorem, and then we'll apply it to the Riemann Zeta function, and then at the end we'll do a little proof if you're interested. The proof isn't difficult. Again, it's a little bit of algebra, but it's not difficult at all. And I did think about not doing a proof, but I think doing the proof really gives you a little insight into the workings of why the theorem works. Right, so let's state the theorem. And it's got three requirements. It starts with the requirement that we have an infinite sum that converges. We'll call that S indexed by J, and it's a sum over K. So there's two indexes here. There's a K and a J. You'll see why that generality is necessary. It might look like we're overcomplicating it, but you'll see why that's the case. But for now you can just think of it as a sum. Actually no, we can say straight away why we need two indexes. We've got n, which is growing towards infinity, it's the sum, and we've got sigma, which is going to be growing to infinity in this case. So we do have two variables, that's why. So first one, we say this sum converges when we sum over k, and here that has to be true for all j. Then we have a second requirement that says the limit as j goes to infinity of this term fkj that exists. That is, if we take j to infinity, the thing doesn't become invalid. There is a form that exists, a closed form or some form. So that means it has to behave normally in some sense. It can't become undefined or explode. So far, nothing too onerous. The theorem is actually quite lax in terms of its requirements, so it means that operation of swapping limits and sums probably can happen more often than not. So let's continue with the third requirement, and this says that this term fkj, that the magnitude of it is bounded by another function, let's call it m of k, which clearly has to be positive because taking the absolute value here, the magnitude is positive. So it's positive, it's always greater than or equal to that, it's independent of the j, so it only depends on k, and the infinite sum of these over k converges. Now that sounds quite a complicated thing to say, but the way to think about it is that there is a normal, well-behaved function, mk, that dominates this fj, this fkj. So because it converges, it says something about fkj that it doesn't behave too crazily, because if it did, then this wouldn't converge. So it's kind of creating an envelope, a bound. We can say that mk dominates this term here. So it's putting a light constraint on that, actually. I know it sounds complicated and the symbols look complicated, but when we go through the example, you'll see how it works and it'll demystify. And you'll see it's actually quite a sensible constraint, and you'll see why it's useful and why it works. If those three conditions are met, if we can confirm that all these conditions apply to a series, then we can take the limit inside the sum. That's the theorem. So let's look at an example now, and in fact let's apply it to our own Riemann Zeta function. So let's start with a series, and the one that makes the most sense is the one that's relevant to the Riemann Zeta series, which is 1 over n to the s. And we are already going to constrain ourselves to sigma more than 1 because we know this doesn't converge anywhere else. So we've already imposed our own limit there. So as far as our working is concerned, this will always apply. So we've got a slight change of terminology here, in the sense that the theorem was stated in terms of f, k and j, and for us it's f, n and s, and sigma is a real part of s. So let's start with this first requirement, which was, do we have a series that converges? And the answer is yes, this series converges, and we have an additional side note to say as long as sigma is more than 1. Great, the first condition is met, as long as sigma is more than 1. Number 2 was, can we confirm that the Fn of s exists when we take sigma to infinity? And so let's do that, let's see what happens. And we've said 1 over n to the s, and we've already seen how the magnitude of this term goes to 0 as sigma goes to infinity, except when n is 1. So we've got a function that's defined under 2 conditions. It's 0 for all n more than 1, and it's 1 when n is 1. And we can say, although that's not something like, sine x or x squared, it's not a polynomial, it's still a valid function, and it does exist when sigma goes to infinity, so that's fine. The next one is, there exists some kind of dominating function mn, which is more than or equal to the magnitude of fns. That's independent of sigma. So we're saying that no matter what sigma is, this mn will always be bigger than that. And actually, there are probably many ways to answer that question. There are many possible mn's and functions that would satisfy that. We just have to find one, and it's usually better to find something that's simple and easy to work with. And actually we don't have to look very far. We can just say that mn is 1 over n to the alpha, where alpha is greater than 1, because otherwise it wouldn't converge, and is less than or equal to sigma, but it's fixed. This alpha is fixed. So we've already found a mn that satisfies this. Mn is going to be, the magnitude of that is going to be more than the magnitude of those terms, irrespective of what sigma is. Of course, we're still mindful of the fact that sigma is always more than 1, because that's the domain in which we're working. So in effect, we've taken it to be itself, but just fixed at an alpha, which is going to be more than 1 and less than any sigma that we choose. So we've satisfied the third condition. Actually, we haven't quite yet. We need to say that the infinite sum of those mn's does converge, and we know it does, because alpha is more than 1. Great. So other examples might actually be easier, where the function here in the limit is a nice closed form like a polynomial or something like that, and the mn might be something that requires less thought, but we are interested in the Riemann Zeta function, so that's what we're doing here. Great, so the conditions are met, so we can move the limit inside the sum. So we can say the limit as sigma goes to infinity of 1 over n to the s, summed over n, equals the sum over n of the limits as sigma goes to infinity of 1 over n to the s. And we know that's always 0, except the very first one. So therefore the answer is 1. So Riemann Zeta function tends to 1 as sigma tends to plus infinity. And in fact, I surprised myself. I thought that we were going to have to say that the magnitude of the Riemann Zeta function tends to 1, and we might have to live with the fact that the imaginary part, or the phase, was circling around 0 to 2 pi somewhere. But actually, no, it really is 1. The imaginary part vanishes as well. So that's quite nice. Great, so we've done that. So that was a little bit of extra work, and it was to justify the slight glossing over that we did last time. So you can stop here if you want, and the theorem is useful, easily stated, fairly easy to understand. But if you're interested in a proof, just to walk through it, then we'll do that now. So this is what we're trying to prove, that the limit as j go to infinity of this sum over fkj is the sum of the limits of fkj. So before we dive in, we just want to show that this thing actually exists. If it doesn't exist, then we can stop working there. So that's our first task. And that's not too difficult. We know by definition that the magnitude of fkj is less than or equal to mk. mk dominates it. That was by definition. That's the theorem requires that. And the theorem also requires that the sum of mk over all the k's converges. That's by definition. So as j goes to infinity, we said that fk exists, and therefore the magnitude of that is also less than or equal to mk. And so this sum of fk, the magnitude, over k's converges. So if a sum over a magnitude converges, we recognise that as absolute convergence of the terms. So when the magnitude of fk converges, we can say that fk converges, and it converges absolutely. And this fk, remember, is the limit as j goes to infinity of fkj. That is what I've highlighted here. That's fk, and that converges when we take the sum over k. So it exists, it converges, it exists. So therefore the sum of the limits does exist. Great. So that's out the way. If the answer was no, it doesn't exist necessarily, then we've got a problem, and we probably have to stop our proof there. Right, now let's show that this actually does equal this. And before we dive into that, we're just going to develop some inequalities that will come in handy. Individually, each of them is really easy to see. The page, I know, looks quite complicated with lots of symbols, but we'll talk through it and show that these three inequalities that we're going to use are quite easy to establish, and then they'll plug into our algebra next. So the first one is just the triangle inequality, which says the magnitude of this thing, which has two parts, a plus b or a minus b, is less than or equal to the magnitude of a plus the magnitude of b. That's you can look that up, the triangle inequality. We've used it a few times before. It's quite common, actually, this technique of establishing inequalities, to use this triangle inequality. Which is funny because we kind of come across it when we're very young in school, and we don't really realise that advanced topics later use it quite a lot. Great. So what we're saying here, that fkj minus fk, and remember this is almost the difference between the terms and the limit fk. Fk is the limit as j goes to infinity. So this is almost like an error term in some sense, or the difference term. It's saying that the magnitude of this difference is less than the sum of those two, which intuitively makes sense as well. Now remember, both of these are dominated by mk, so they are less than or equal to mk and mk, so that's 2mk. So this thing is less than or equal to 2mk. That looked complicated, but quite easy. The next inequality we're going to develop requires us to think about this sum, mk. Remember, it was an infinite sum, and because it's an infinite sum that converges, the terms tend towards 0, as in the tail of this series gets smaller and smaller and smaller. So it might be, let's just imagine, 10 plus 5 plus 3 plus 2 plus 1 plus 0.5 plus 0.005. And you can see as those terms get smaller, we can find a cutoff point so that the sum to the right of that, beyond that, is always less than some arbitrary value that we can think of. And quite commonly it's called epsilon. That's the tradition. So we're saying if we pick a starting point n, as long as n is large enough, the sum from n to infinity of k of those terms mk is less than some epsilon. And the idea is to make this as small as we like. So if this was, say, 0.0001, we can find an n where this is true. It might be a large n. If this was 0.00000001, we can still find an n where this is true. So we can make this epsilon as small as we require. It just means the n has to be big enough. So the magnitude of that series fk of j from n to infinity is, so we've taken the magnitude outside the sum, and that's, if we apply the triangle inequality but with many terms, not just two, it's less than or equal to the sum of the magnitudes. Let's say that a different way. The magnitude of a sum is less than or equal to the sum of the magnitudes of the individual things in that sum. That again is a slight generalization of the triangle inequality, and that again makes intuitive sense. So that's all we've done here from there to there. It looks complicated, but when you say it in plain English, it's not at all. Now remember, this thing is dominated by mk by definition. So we've come to this expression so far, which is here less than epsilon. So it's saying that we can make this quantity less than epsilon. Now if we say j goes to infinity, we know that fk exists. So all we've done is copied this, pasted it, and replaced fkj with just fk, because when j goes to infinity, fk exists. And it's a simple parallel to say the magnitude of that sum is less than the sum of those magnitudes. It's dominated by mk, so it's a sum there, which is less than e. So we've got two inequalities here. This one less than e or epsilon, and this thing less than epsilon. And of course the very first one we developed here. This is just a bit of side work where these inequalities will help us with the algebra in the next step. So let's go and attack the problem. We're going to consider the absolute difference between the sum overall k of fkj and fk where j is in the limit infinity. And although this rest of this page looks complicated, what we're really doing is simply splitting this sum from k of 1 or 0 to infinity into two. So it's going to go from 0 to n minus 1 and from n to infinity. And the reason for doing that is because, remember, we said n to infinity, those sums can be less than epsilon, as small as we require. That's why we're splitting it into two. So let's look at what's happening here. Again, it looks complicated, but it isn't. These are the two sums that we are interested in. We have taken the absolute value of their difference. Here, we've not done anything except split the sums from 0 to infinity into 0 to n minus 1 and n to infinity. And you can see that here, k n minus 1 and then n to infinity, and then for the second term it's k to n minus 1 n to infinity. So it looks complicated but isn't. Now we're going to apply our inequalities. No, not yet. No, not yet. We're going to look at this entire thing, which has got an absolute operator around it, absolute value, and we're going to use our triangle inequality again to say the magnitude of these three things is less than or equal to the magnitude of the individual three things. So when I say three, it looks like there's four. The three things we're going to look at are this thing here, and we'll keep those two together as the third item. So by applying the triangle inequality, we can say the magnitude of all that is less than or equal to the magnitude of the fk j sum from n to infinity, and this and also the magnitude of this sum here, fk from n to infinity, plus the magnitude of this quantity, which is still keeping those two tail sums, not the head sums, together. Now we know from before what we did here, this quantity is less than epsilon and this quantity is less than epsilon for large enough n. That's this one and this one. So we've got epsilon and epsilon, so that's less than 2 epsilon. And all we've got left is this thing here. Now this is a finite sum. It's not infinite. It goes from k starting at 0, 1 up to n minus 1. And we have to think about the magnitude of that difference. We just collected the terms here. So because it's a finite sum, we can take the limit inside the sum. So as j goes to infinity, the finite sum, finite, does go to 0 because fk, as j goes to infinity, becomes fk minus fk 0. So that tends to 0. We've taken the limit inside because it's a finite sum. So that removes that from the expression that we had. So we're left with now the limit as j goes to infinity of that big difference that we were interested in, the magnitude, is less than 2 epsilon. Now remember, epsilon can be as small as we require. So this is saying that in the limit, this magnitude of the difference of these two quantities is less than any epsilon that we can think of. In effect, the difference is 0. So that's quite a common technique, this epsilon technique, and it's used quite a lot. Slight variations, but it's used quite a lot. And we've just done an example of that kind of analysis here. So what that's saying is that if the magnitude of the difference between these two sums is less than any quantity that we can think of, they're effectively equal, because the difference can be, effectively 0. So in the limit, as j goes to infinity, we've shown that fkj is the sum over of the k's of fk, and that proves the theorem. Let's write that out in case that jump wasn't clear. The limit as j goes to infinity of fkj equals the sum over k of fk. That's what we've shown here, which is fk is the limit as j goes to infinity of fkj. Lots of f's, k's and j's, but when you see it on the screen, hopefully you can see what's going on. So I hope that wasn't too complicated. What I recommend actually is if you want to really understand this, is not just listen to me talking it through, but to write it out yourself. If you write it out by hand and try to work the next step from the previous step, and if you get stuck, come back to this video and hear the explanation of how we can go from one step to another. That will help you understand it. So I hope that was useful. It was something that was just bugging me a little bit as to why we can make that easy analysis by swapping the sum and the limit. And others online pointed out that actually that wasn't always possible. You have to justify it. So thank you to all the people who commented. I hope this was useful. Great. See you next time. Bye.